Hi, this is the video for our lab titled The Kinematics of Rolling Motion. In this lab, we created an experiment to observe how changing the incline angle, the height, and the mass of our objects will affect the motion and the timings of a rolling object, and then compare our results with the expected kinematic model.
Hey guys, so this is going to be the theory for our experiment. First we're going to be talking about the conservation of energy. As you know, that in a closed system, the potential energy equals what the kinetic energy used to be. The two components of that are the translational kinetic energy and the rotational kinetic energy. The potential energy formula is mgh. The k translational is half mv squared. And the k rotational is half k mr squared, which this is inertia. So as you see, there's m in all the terms, so m should cancel out. As you see here, we rewrote omega squared for v squared over r squared, because omega is just v over r. So if you square both of them, you get this. But then r squareds cancel, and you get left with half v squared. Gh equals half v squared plus half kv squared, which then simplifies to half v squared parentheses 1 plus k. And now we need to figure out what v is. Okay, so the next part we need to do is find the velocity for our equation that we found here. So let's talk about what we're going to be doing for the experiment. So we have a ramp here that we have the object starting with a velocity of 0. The distance here that has to travel can be described as h over sine theta. And when the initial velocity is 0, you have this relationship that the acceleration that you have times time equals the final velocity. To get that all together, we can finally use another equation, which is d equals half acceleration t squared. Let's use all of these together to find the final velocity. So first, let's try to find the acceleration. Acceleration, if you rearrange this equation, is equal to 2d over t squared. We can replace the d with this right here, which is h over sine theta. We get acceleration is equal to 2h over sine theta t squared. You can plug in this acceleration for the acceleration we have here, and that gives you 2h sine theta t squared times time. As you can see, these cancel, and then you get left with final velocity is equal to 2h sine theta t, dependent on the height we have here, the angle where it's at, and that's how long it takes has to do with the velocity. Okay, so now we're gonna put everything together. Now that we know that the v final equals 2h over sine theta over t, we can replace the v squared for that, and then you get this equation. See, the v squared is now replaced by 2h over sine theta times t. And then you can do some algebra, which I will not show here because it takes a long time. You get t equals 2h parentheses 1 plus k over sine squared theta g. To experimentally prove this formula, we are going to do 3 different activities. Well, I didn't include one because we're going to disprove mass. One of them, we're going to use height as our independent variable, and we should get an exponent of half. And then the next one, we're going to get sine theta as our independent variable, too. And then we're going to get time as our dependent, and this relationship should be true. And we're going to pick one of these activities. For this experiment, we're going to use this second activity. We're going to try to interpret the k for each material that we're going to be using by using the concept that this coefficient must be 2h over g times this expression. And from this expression, we can algebraically find k.
Alright, for our lab today, there's a little bit of equipment that you will need. First, you will need a ramp next to our cylinders. For our lab, we're using this cylinder here. Another thing you will need is something to measure with, so you can look at different heights. And along with your different heights, you'll need something to measure your angles, such as a goniometer. And to help with your ramp, you'll need something to support it on, which will allow you to change your angles. Here we have a metal block and a bucket to use. This you can use whenever you have. Also, you will need something as Excel to plot your data and to help you come up with your graphs and information. And to get the masses, the things you need for your balls and your cylinders, you'll need a scale to do so, such as a mechanical scale or an electronic.
We begin this experiment by measuring the mass of the 3 balls we will roll down the hill in Activity 1. We then measure the slope of the hill and proceed to roll the 3 balls with different masses down the hill and record their times. We then choose 5 different points on the hill and roll down a metal ball and a metal cylinder to see how the height will affect its time to reach the bottom. Finally, for Activity 3, we choose different slopes and roll that same metal ball and metal cylinder down to see how the slope will affect the time it takes for the objects to reach the bottom.
Okay, so now let's talk about the results and the conclusion of our experiment. So our first activity was successful as there was no correlation between the mass and the amount of time it took for an object to roll down a ramp. As you can see, our ideal value was a 0, flat line, and the exponent we got was 0.034, so this was our absolute error. Now, we changed the height of the ramp, but kept the angle the same. So we did it on different spots in the ramp. And for the marble, we got a good percent error. It was accurate. As you can see, this is our power, this is our ideal value, as we saw in the theory. And the coefficient was also good. This is how we calculated the ideal value. So they were both accurate, as there were fairly small percent errors. And our R-squared value was good, as it was precise, close to 1. Same thing for the cylinder. The power was this. Compared to the ideal value of this, had a percent error of 4.32, so it was accurate. And the R-squared value wasn't that great, so the precision was not as good as we wanted it to be, but it's still acceptable as it is over 0.9. Percent error for the coefficients also pretty significant, but it's still well below 15%, so we can still use it. Our percent error for the coefficient was 7.9%, which is not great, but it's still reasonable because it's below 50%. For activity 3, we changed the angle of the ramp with the same height. So for activity 3, we varied the angle of the ramp and kept the height the same. This is the power that we got with the expected value of this from the theory, -1. There's our percent error. Our coefficient had a big percent error, so we explained that in the conclusion. It was still below 15%, but it's still concerning. Similar thing for the cylinder. The power that we wanted was -1. This is the percent error. This is the power that we got. As you can see here, both of these had really good precision, 0. Very close to 1. And the coefficient obviously was like this, so it had almost a 12% errors. Now for activity 4, we picked activity 2, but you can pick any of the activities, and we just did some algebra from the coefficient to find the k value. So we had the coefficient that we calculated earlier. We took out the square root 1 plus k. Then algebraically, we found this, as you see here. We got a value of around 0.3, which is around 25% off from the theoretical value of 0.4. So there is a good amount of systematic error there. Similar thing for the cylinder. We did the same process, and we got a k value of 0.716, which again is very off from it's 28.45% off of the theoretical value of 1. For the cylinder, one explanation that some systematic error that we can have is that the k value isn't truly supposed to be 1, as it is not a perfect hollow cylinder, but it's somewhere between a disk and a hollow cylinder, and the disk has a k value of 0.5. So it should be somewhere in between, maybe not that low, it should be closer to a hollow cylinder. But another systematic error that applies for both the marble and the hollow cylinder. First, air resistance could influence it a lot. Friction, you can hear the sound, so the energy transformation that was occurring there had to do with friction. And also the timekeeping, there was human error every time we kept the time. So that could have influenced our results negatively. Anyways, thank you so much for listening and have a great day.